so now we're going to talk about the transform of a derivative. Okay? Now, by doing the transform of a derivative, initial conditions are inserted into the problem. So this first one we're going to do, we're just going to talk about the first derivative, where we're going to do the Laplace transform of the derivative. This is the transform. That's our f of s. We're going to try to, that would be the transform of just y by itself. Okay? And then the nth derivative, the transform of that, is s to the n, and then this is the transform of just our regular y. And then we incorporate all of the initial conditions with these s's decreasing in power so that we can introduce the initial conditions into the problem. Okay? Now, by doing this, when you do the Laplace transform, and the Laplace transform inserts the initial conditions into the problem, whenever you do the inverse Laplace transform, well then, bam, you got the answer right there because you already inserted the initial conditions into the problem. So in our normal methods, we would, let's just take a normal homogeneous differential equation. What you would do is you would look at the auxiliary equation, find the roots of that auxiliary equation. Now that auxiliary equation would tell you what type of solution you would be looking for, but there would be these constants, the C1, C2, C3, that would be introduced into the problem. And then you would have to take the initial conditions at that point and solve for those constants inside of the problem. Now, when doing this with the Laplace transform, by doing the Laplace transform, the initial conditions are already inserted into the problem. So that when you do the inverse Laplace transform, there's none of this business of trying to find these constants based upon the initial conditions, because the initial conditions were already inserted to the problem through the Laplace transform. Okay? So let's take a very basic sample and see what we have. So, okay. So let's say we just had this differential equation right here. dy dt minus y is going to equal 1. And the y of 0 is going to equal 0. Okay. So what we're going to do is we're going to do the Laplace transform on this differential equation, and then we're going to do the inverse Laplace transform of this of the Laplace transform that we did, and we're going to get the solution to this differential equation. Okay. So let's just go ahead and say, all right, I'm going to perform the Laplace transform on all of these. Okay. Now, you can see from up here that if I do the Laplace transform just dy dt, I'm going to get s of f of s and then minus y of 0. Okay. So this becomes s f of s minus y of 0. Okay. And the Laplace transform of y itself is just, that's our f of s. And the Laplace transform of 1 is just 1 divided by s. Okay? Okay, so we have our initial condition right here, that y of 0. But y of 0 equals 0, so let's just make that one disappear. Okay, so that would be s f of s minus f of s, which is going to equal 1 divided by s. Right? Now, the point of this is to get f of s by itself. If you get f of s by itself, you can do the inverse Laplace transform on it, and you'll have your y. Okay? So let's go ahead and let's pull that f of s out, and this just becomes s minus 1, which equals 1 divided by s. Okay? But we want f of s isolated all the way by itself. So f of s is going to be 1 divided by s times s minus 1. Okay. Okay, but I don't remember there being a Laplace transform of an inverse of 1 divided by s times s minus 1. So we're going to have to do something to this. And think back to when we were doing integrals in calculus 2. If you were going to try to integrate something like this, what would you do? You would do partial fraction decomposition to break it into its individual pieces and then integrate the individual pieces. And so we're going to do the same thing on this one. So we're going to have to do partial fraction decomposition. Okay. So what we're going to have 1 divided by s times s minus 1 is going to equal a divided by s plus now b divided by s minus 1. Okay. Now let's multiply by s times s minus 1. That's going to give me 1 is going to equal a times s minus 1 plus b times s. Okay. So this one's pretty straightforward. So let's go ahead and let's just choose the values. So if I let s equal 1, well, this term right here is going to completely disappear, and I'm just going to get that b equals 1. Okay. If I let s equal 0, okay, if I let s equal 0, that b is going to disappear, and I'm going to have a negative 1 right here. So what is that going to give me? That's going to give me that a is going to equal negative 1. All right. Okay, so what are we getting from this? We're getting that f of s is going to equal negative 1 divided by s plus now 1 divided by s minus 1. Okay. Now that we've done this, we can do the inverse Laplace transforms of these two guys right here. And the inverse Laplace transform of this guy is just y. So we're going to do the inverse transform at this point. So L inverse of f of s is going to equal negative now L inverse of 1 divided by s plus now L inverse of 1 divided by s minus 1. Okay? Now the inverse of the transform is just y of t. Okay? Okay. 1 divided by s is just 1, so that would turn into a negative 1, and then plus e to the t. Okay, that's 1 divided by s minus 1. 1 divided by s minus a is e to the at. So our a is just 1. And that's it. That's the answer to the problem. So what did we just do? We took a non-homogeneous differential equation with an initial condition. We did its transform, which introduced the initial conditions. Then we did the inverse transform. And after we did the inverse transform, we're done. And that is the solution to the problem. So this is one of the reasons that the Laplace transform is so nice, is that you do the transform, go into the frequency domain, basically just do partial fraction decomposition, break everything into its individual pieces, do the inverse transform, and you got your answer right there.